Hey everybody, in this video we're going to cover our first example of conservation of energy. Let's go ahead and start by reading the problem. Starting from rest, a 25 kilogram child zooms down a frictionless slide from an initial height of 3.0 meters. What is their speed at the bottom of the slide? Alright, so starting off, let's identify the information that we are given. The mass of the child is 25 kilograms. The initial height of this problem is going to be 3.0 meters. The initial velocity is going to be 0 meters per second because the child is starting from rest. And then the problem is asking for how fast will they be when they reach the bottom of the slide, right before the bottom of the slide. If we try to draw this out as a sort of right triangle, I can draw a free body diagram, but you realize looking at this right here that I only have the initial height, and sure I can draw the force of gravity, but because of the lack of angle, kinematics isn't really an option here. So since we don't have that information, this is where conservation of energy kind of comes in very useful here. Using the conservation of energy law, the law says the mechanical energy at the beginning equals to the mechanical energy at the end. And mechanical energy is defined by the sum of both kinetic and potential energy. So if we express that, we are going to write this as initial potential energy, UI, plus the initial kinetic energy equals to the final kinetic energy plus the final potential energy. Well, we know how to define kinetic energy. Kinetic energy is defined by 1/2 mv squared, right? And then the v changes based on whether you're talking about initial or final kinetic energy. The next thing we have to do is identify what potential energies are in our problem. Are we dealing with any springs? Are we strictly dealing with gravity? And for this problem here, since we're talking about a child going down a slide, there are no springs involved. So therefore, the only and the reason the child is going down the slide is because of gravity. So the only potential energy involved is potential energy due to gravity. So recall earlier that we said the initial velocity is 0 because the child is starting from rest. Because the initial velocity is 0, that means the kinetic energy initially is 0 as well. So you can kind of cross it out or just cross it out to a 0. In addition, the child reaches the bottom of the slide, and that allows us to define the final height as 0. And with that, we can kind of knock off the final potential energy because the final height is 0. Doing this, the only thing that we're left with here is the initial potential energy and the final kinetic energy. Right? And those two values have to equal each other. All right, and we can write this as mghi equals 1/2 mvf squared. Looking at this expression, we can easily cross out mass conveniently. Right, and then plugging things in, we are going to have 9.8 meters per second squared due to gravity times the height of 3.0 meters equals to 1/2 times the final velocity squared. We can work this algebraically, and then we can find out that at the bottom of the slide, the child is going to have a final speed of 7.66 meters per second. And that concludes our example on conservation of energy. Thanks for watching.